Our next speaker is Alina Kuznetsova, who is currently at Google. Prior to that, she was at PhD at the University of Hanover, and before that, she was in Moscow at CMC SU. Alina will be talking about her work done at Disney, right? As an intern at Disney. It was presented at ICC 15, right there. Okay. And it will be about gain detection and about videos.
Yes, thank you for the introduction. As Victor said, I will be presenting a joint work done with Sunju Wan, now in Ulsan National Institute of Science and Technology in Korea, and with Leonid Sigal, who is still in Disney Research. First, let me introduce the problem of domain adaptation. In a classical machine learning setting, it is assumed that samples on which we train a machine learning model and the samples on which we apply this machine learning model come from the same distribution. This is a basic assumption under a machine learning. However, this is not usually a real-world situation, and in this case, basically, the samples on which we train our model come from one distribution PS, and however, when we apply the model, the samples might not come exactly from the same distribution, and so this causes the degradation of the performance of the classifier of the detectors that we are training on the target domain. So, and in this case, basically the training domain is called source domain, and the target domain is the domain where we apply the model. So there are several examples that when this problem occurs. Firstly, for example, in speech recognition, when we train our model on one subject and apply it on another subject, or we train the model on a set of people and apply it on another set of people, then recognizing speech is, so it performs worse on another set of people. Then another example comes from natural language processing, where, for example, if we try to perform sentiment analysis on different texts, the model trained on, for example, news text will perform worse on the text coming from informal comments on YouTube, for example. Finally, this problem also occurs in computer vision, and this is one of the cases of this problem I will present in my present here. Let's speak about a classical scenario of object detection in still images. So in this case, we can assume that both train samples and test samples come from the same domain. So basically, the appearance of the let's say, composition of the images, viewpoint, lighting is more or less the same for both training data and test data. However, when we have to work with videos, it can happen that the appearance of objects in videos is drastically different from the appearance of object in images. So this might come from different, so from a motion blur, from, let's say, unexpected viewpoints, from image distortion, from weird lighting conditions, so etc. So there might be any reason. So on the slide you can see that objects look very different in video data and in image data. So consequently, this difference will cause a decrease of performance of the detector if it is trained on images. So let me introduce some related work on domain adaptation. These two methods, geodesic flow kernel for unsupervised domain adaptation and transfer geoanimation for unsupervised domain adaptations, are recent works that basically tackle the problem of unsupervised domain adaptation, where we have labeled samples on the source domain and we have unlabeled samples of the target domain. So what these two methods do, they basically try to match distribution, general distribution of the features, disregarding the labels in the target domain to the source domain. In practice, it means that there is a transformation found from the source domain to the target domain that transforms the features from the source domain to match the from the target domain to match the distribution in the source domain. Now I will introduce two works that are probably closest to my work. So first work is shifting weights, adapting object detector from image to video. So in this work, the same problem is basically addressed, and what they do, they use they first train a detector on the image data, and then they use it to select good samples from the confidence samples from the target data, and then they use these confidence samples to update their detector, and they also weight the samples gradually. So during training, the samples have more and more weight. During the training of the detector, and that means that the detector gradually shifts from the source domain to target domain. So the second work, semi-supervised domain adaptations with instance constraints, uses the fact that in videos usually the same instance of an object appears. So they use a small set of label data, and they find similar objects in the target domain, and they basically build the constraints, additional constraints when they train their detector based on this similarity between samples in a target domain. And this allows them also to build detectors that performs well on the target domain. So now the question is, what else can we do? So one problem that is not addressed by the previous works is, in general, the intuition is that if we see more data, even if this data doesn't have labels, it potentially should allow, we should be able to improve our detector continuously with seeing more and more data. So, and basically we also want to improve, potentially as we see more data, we want to improve not only on one domain, but on the domains that are similar to this new domain that we've seen. So how can we achieve this? And there are two key ideas. So first idea is that to be able to kind of continuously improve the detector, we want to dynamically adjust the complexity of the detector as the detector sees more data. And the other idea is that concerns how do we select the samples for improving the model. And we use basically temporal consistency to extract informative samples from video to train the model. So let me give you an overview of the framework. So we firstly start with a detector trained on static images coming from ImageNet. Then we And then we start to process unlabeled video data coming from different domains one by one. I will talk about this in detail later. We select good samples from this unlabeled data according to our current detector, and we use these samples to increase, to update the model and to increase the complexity of the model. So this is an overview of the framework. Let's start with the basic detector that we are using. So the basic detector is based on large margin embedding. So the original large margin embedding paper was published in NIPS 2009. Basically, the idea is that given us feature representation of the image patches, we firstly find transformation to project these features to the low-dimensional space, such that the classes are well separated in this space. So additionally, we also learn a set of prototypes in this low-dimensional space, one per class, such that each prototype represents a class, and basically classification is done in this low-dimensional space by measuring similarity to the prototypes. To learn this, the mapping from the high-dimensional space to the low-dimensional space and the prototypes, we have to minimize the following functional, giving two sets of constraints. So first set of constraints is interclass constraints, which basically says that the prototype corresponding to one class, so the sample corresponding to one class should be close to the prototype of this class and to all other prototypes. Another constraint is the detection constraint that requires all the samples from that don't come from any classes to be far from all the prototypes. So after minimizing this functional, we basically learn the matrix W and U. So now the question is, how can we extend this model to be able to learn more? How can we extend this model? How can we increase this model's complexity? So the natural way to do this is to introduce multi-prototype extension of a large margin embedding model. This is based on, so if you think about it, this is a very natural extension also because having a single prototype per class would mean that we have a unimodal distribution of features for this class, while it's natural to expect that it is multimodal, especially if the data is coming from multiple domains. So in this case, we extend the model to have multiple prototypes, and in this case, what changes is basically the similarity measure between the sample and the prototypes. So how do we classify that the sample comes from a class? For this, we basically take a maximum similarity. We take the closest prototype and check its class, and this is represented by using smooth maximum approximation of the similarity measures that we used for single prototype model. Given this extension, we can actually learn the new prototypes on the fly as we see more videos. So in this case, it means as we see more data, we increase model complexity. To learn these new prototypes, we as well optimize this kind of functional, and there is a new set of constraints. So basically, the first constraint requires that the new prototype is representative for its class. The second set of constraints requires that this new prototype doesn't prevent the right classification for the data that we already seen. And finally, we still have a detection constraint. Okay. Now, as I described how we do online updates, I will describe how to actually select the good samples to update the model, right? So until now we assume that we are just extracting somehow from videos. Here we do something similar to what the previous speaker was doing. We basically extract tubes from videos using a seed the confidence detections of the model, of the current model. So firstly we run a selective search object proposals on each frame with a frame rate 1 frame per second of the video, and we select the confidence detector. We score these object proposals based on the current detector. We select the most confident object proposals, and then we use a quality tracker to propagate the object proposals in time to select the tracks. So afterwards we score the whole track based basically on the confidence of all object proposals on this track. And we accept or reject track based on the final score. The reason why we do this is basically because if we select the samples that are not that are scored with low confidence from the detector, then from one side this will be most informative samples, but from another side we can easily make a mistake. And if we select the samples with only high confidence, then we basically don't add new information to the model. So now I will move to evaluation. So I evaluated this proposed method on 2 datasets. First dataset is the dataset activity daily living dataset. This dataset contains 20 videos, 20 egocentric videos, each of about 30 minutes long. Here I selected 8 most common categories in these videos. And as a baseline, we used, I used a deformable part model. So this is just a baseline provided with this data set. As a domain adaptation baseline, I used geodesic floor kernel. And then these 3 baseline come from our work. So LMED is basically basic detector trained on images. ID LME is a detector trained. The model that we get after processing all the videos, and LMEA is a baseline where we would take the LMED model and do the same steps for sample selection as for ID LME model, and but just adjust model parameters instead of adding new prototypes. So here you can see that here I show the best performing class from this data set, the worst performing class, the detection mean average precision on the whole data set, so this all mean average precision, and also the accuracy on ImageNet. So there are 2 things to notice here. So firstly, if the detection performance is good enough on the class from the beginning, then the model improves a lot. Unfortunately, if the detection performance is not that good, like for example for the class SOAP, then the model doesn't learn anything useful. Unfortunately, basically it means that there should be some overlap between the, let's say, significant overlap between the training samples and on the source domain and the target domain. So the second thing to notice is that on ImageNet, as you can see, our I call it domain adaptation baseline, where we don't increase complexity of the model after adapting to the ADL dataset. It performs worse, which is expected. However, the model that has seen all the videos actually also improves its performance on ImageNet. So it improves its performance slightly on the source domain as well. And so this is basically the effect that we wanted to achieve. Okay, so here are some examples of the detections on the ADL dataset. You can see that the data is quite challenging, and you could also probably notice that the average precision is not that high for some objects. So and as you can see, it also differs a lot from the target domain of ImageNet. So the illumination conditionals are different. There is a distortion. The viewpoint are kind of very different from source domain. And so below you can see the projection of the learned model. So here is basically the bigger circle shows the starting prototype, and the rest is the prototypes that are learned by the model. So the second data set that I evaluated this approach is YouTube objects data set, which contains the short clips from YouTube videos. There are 10 classes, and here, so problem with this data set was also that it contains only one bounding box per shot. So if you have a video, there is only one bounding box annotated there, so it's harder to measure the performance. However, as you can see, so our model also improves on this data set as well on average. For some classes, the performance also improves a lot. However, on this data set, domain adapted model actually performs on average slightly better than the more complicated model. However, domain adapted model again performs much worse on ImageNet, and IDE-LME performs much better on it performs slightly better on ImageNet than the original model. So takeaway from my talk is that basically unlabeled data can be very useful to increase model performance, even if the labels for this data are not available. So some future research directions are the following. So firstly, the full model can be implemented as a neural network. Obviously, there was something similar on ECCD 2016, where the authors proposed to train a multitask model, each time adding a new task, and train it in a way that the data that was previously used to train the previous tasks is combined with the new data in a way that the labels that the model gives to the old data are preserved. So in this way, basically, the training is kind of regularized, and the model doesn't drift towards the new task only. So the second future direction is how to select samples to train the new model and not to introduce the drift. In this case, basically there are two ways to do it. Firstly, it's in unsupervised case, how do we, so that's very important how we select samples so that we do not introduce any drift. And there is also, if we have opportunity to use some supervision, how do we select the best samples to get the most effect for improving the model performance? And finally, the question is also how, in which order should we, if we have a lot of data, in which order should we give the data to the model to make it learn better? So that's it. Thank you for your attention.
Thank you. One question, you were transferring the task of image recognition in boundboxing, to video recognition in boundboxing. And one aspect of video is that if you apply your algorithm per frame, the smoothness of the predictions you get is a concern. And did you address it in any way?
You mean smoothness in terms of the scores of the detector?
No, I mean in the bounding boxes predicted in subsequent frames.
Yes, sure. So that's so this was the tracking part. As I said, basically we score the bounding boxes and we select the confidence samples, and then for each confidence sample we build a track. And we score all bounding boxes on this track.
But as I understood, it was used for selecting the samples that could go into the training.
Yes.
And for example, based on the procedure, the more confident ones would be selected, so more static ones that are not prone to those unsmoothness problems.
Not necessarily. So the goal of this procedure is So the goal of this procedure is actually to select the samples for which classifier doesn't have high confidence scores. So basically, if you have the whole track is accepted, you take all the samples from this track to update the model. Does it answer your question?
I see the the constraint that prevents the model in the end to deliver non-smooth inferences from frame to frame.
Oh, yeah, sure. So the model is, the detections come on a per frame basis. So basically, after having this constraint, after taking on the samples from the track, there is no other constraint. So if you apply model without the tracks, there is no guarantee that it will select the samples consistently across frames.
So in testing, the tracking was also applied, yeah?
Sorry?
In the inference time, when evaluating, some tracking was also applied?
Yes.
Thank you very much.
Questions? Just a quick one. So how is this then related to the centric activity recognition? If you can answer, of course.
I guess I can. So they basically have a lot of videos from Disney parks, and they want to do all kind of stuff with these videos.